Okie dokie. All right. Before we begin today, are there any questions? All right. So I wanted to look at that last example in chapter 2. Excuse me, before we start chapter 3 today. I blame this on COVID brain. Why not? I do have to say that I don't know if it was the infusion or what, but I've only had 2 days of sick. The rest of the symptoms have been so mild, I could blame it on allergies, to tell you the truth. So I'm very, very fortunate that I'm old and qualified for the infusion. So anyway, but I did want to look at this example because I think I did a poor job last week on this example. All right, so this is the example of the 31 scores from a spring pre-calculus class. And we want to take these 31 scores and calculate the measures of the center of our data. So we want to calculate the mean, the median, but we also want to look at the standard deviation. So the easiest way to do this is to put these values in our calculator. So I took these 31 scores and I put them in a list in my calculator. So I put it in L1. Okay, open my calculator up. So if I go to my calculator and I go to my stat menu and I go to edit, there's those 31 scores. They're in my first list. So I cleaned everything out. I had such a mess last week. I cleaned everything out and started over again. So now I'm going to calculate the one variable statistics for this list of data. So I'm going to first exit. Once I put my numbers in my list, I need to exit out of that list to actually do the calculation. So I'm going to do a second quit. Now I'm going to go back into my stat menu and I'm going to arrow over one to the right to the calculate menu. And I'm going to calculate the one variable statistics on that list. Okay, so I put my data in L1. I didn't use a frequency. So all my data is in a single list. So my list is L1. My frequency list is empty. So if I had anything in there, I could just delete that out. And now I'm going to calculate. All right, so the mean score of this data is 73.5. So that's the average. The average on this test was 73.5. But if we remember looking at the data went from 33 to 100. So someone made a 33 and someone made 100. So the standard deviation, which is the S sub X down there, that's the sample standard deviation. And if we assume that this class is a sample, not a population, we would use S sub X. Now, if we assume this class is a population and not a sample, we'd use the next value down, which is sigma. And they're calculated slightly differently. But let's just assume this is a sample. So the standard deviation is 17.9, which is a pretty big number, which indicates to us, since it's such a large number, that we are getting a lot of variance or a lot of variability in our data. Remember, the standard deviation is a measure of how much each data point deviates from the mean. So the mean being 73.5, it's a measure of how much each of these points deviate from the mean. So we can see from our data that the minimum value was 33. Our first quartile was 61. That means 25% of our data values are below 61. The median was 73, which means that half of our data is below 73 and half of it's above. And the median and the mean are really close in value. And that actually doesn't necessarily surprise me, because when we're talking about scores on tests and things like that, I would kind of expect the median and the mean to be close together. The third quartile is 90, which is interesting because that means a full quarter of our scores are above 90. Well, that's pretty good. That's pretty good for a test. All right. And then our maximum was 100. So we had scores from 33 to 100. And then we can look at our quartiles and how that breaks our data up into quarters. Now, the next thing I wanted to do was to actually graph this data using both a box plot and a histogram. So I'm going to go to my stat plots. So second stat plot, second y equals, and I have plot 1 on. So I'm going to hit enter. And plot 1 that I have turned on is a box plot. So you can see in the next line down from the on off, the type that's highlighted is my box plot. My X list where I put my data is in that first list, L1. Now, since I didn't use a frequency table here, the frequency I need to put in as the number 1. If I put this data in 2 lists, where one list were the data values and the second list was the frequency of those data values, then I would use the frequency of whatever list that's in. Okay, so I have that plot on. Now, I want to turn on the same graph. I want to turn on a histogram. So I'm going to arrow up to my plots, and I'm going to arrow over to plot 2, and I'm going to hit enter. Now I'm going to turn plot 2 on, and that's going to be my histogram. So it's on, you can see the cursor blinking on, and the type, the histogram is highlighted. The data I'm going to use is L1, and the frequency again is 1, because I don't have my data in a frequency table. I have my data in just one list. Okay, so now to get the histogram to look the way I want it to look, I'm going to adjust my window. And so my smallest data value was 33. So I'm going to start my window in the X direction a half a point below that, which is typical of what we do with histograms. So I'm going to start my graph at 32.5. My largest value was 100. So I'm going to end my window at 100.5. Now the scale, the 13.6, was found by taking the difference in the maximum and the minimum window and dividing it by the number of bars I wanted in my histogram. So if we go back to our slide, we had decided we wanted 5 bars in our histogram. So what we do is we take the 100.5, we subtract 32.5, and we divide that by 5, and that'll give us the width of these bars. And you can just type that in. I already have it typed in, but you can type it in and your calculator will calculate it for you. So I typed it in with parentheses, division by, I want to divide by 5 because I wanted 5 bars in my histogram. So my scale is 13.6. Now the minimum and maximum, they chose that for you in the slide. This is a number that you can just play with until the graph looks the way you want it to. I don't know that there's anything sacred about starting at -2.4 and ending it at 17. I don't know that there is. And we're going to use a Y scale of 1, 2. So now that I've got my window set up, I can hit the graph button. And I can look at this graph, and this is going to tell me some stuff about my data. So if I turn on the trace, hit the trace button, the trace, when I turn that on, it blinks on the median. So again, you can see the median is 73. If I arrow to the left, I can see the first quartile is 61. So I have a full quarter of my data is below 61. Okay. And then I can arrow back to the right. Now let's go back over here. So you can see that the first quartile is at 61, but the minimum is at 33. So the first quarter of your data, the range is from 33 to 61, which is pretty big. So you get that long stem there, that long line that shows you have quite a bit of difference in the minimum value on your exam and your first quartile. That 33 is really a low value and it's affecting everything, right? So then we can just arrow over and we can see that the third quartile is 90. So you have a full quarter of your data is above 90. That's pretty good. So it kind of tells you, you got actually more people scoring higher than you have scoring lower. As a matter of fact, your median, you got 50% of your class is scoring above a 73. So that's pretty good that you got half of your class scoring above 73. And then you can see from the histogram below that you actually have a nice tall bar over there at the end. So let's use our arrows and let's go over there. You've got 11 people that's scoring B or higher, 86.9 and higher. So you've got a lot of people is scoring pretty high on this exam. So just looking at the two plots, you can tell quite a bit about your data that you just didn't see if you just look at the list of data. So a picture can really help you sort out what's going on in your data. It's a good idea every time you take data to graph it. Use some kind of graph, either a box plot, a histogram, a line graph, some kind of graph so that you can see the trend in your data. Right. All right. Standard deviation of grouped frequency tables. Now, if your data is grouped, that means you have your data grouped in classes where you have a minimum, a lower class limit and an upper class limit. And then you determine how many data values are in that class, in that range. So that's grouped data, where your first column is a series of classes, and the second column is the number of data values that are in that class. Now, when you calculate statistics from grouped data, you don't get exact values because it's grouped. And what we use is we use the midpoint of our classes to calculate our statistics. So we have here an example where we have 6 classes over here on the left. And we have the frequency or the number of data values that are in each of these classes. So for example, we have the first class goes from 0 to 2, and we have a frequency of 1. So 1 data values between 0 and 2. 6 data values are between 3 and 5. 10 are between 6 and 8, etc. Now, you can't put this in your calculator in classes. So what you have to put in your calculator is the midpoint of each class. So you just take the lower class limit and the upper class limit, you add it together and divide by 2. And that's the data that you put in your calculator. So in your first list, you would put the midpoint of your classes. And in your second list, you would put the frequency and then calculate the one variable statistics based on that. Now, honestly, if you're the one taking the data, you have the raw data before you ever set it up in a frequency table. You know your data, so you can calculate the statistics for your own data. You're not typically going to be given data that's sorted or like this. You're going to actually collect your data. But if you're doing a retrospective study for data that's already been taken, maybe it is presented to you in this fashion. And if it is, you can still calculate statistics based on that data. You're just not getting an exact value because you're using a midpoint and not the actual data values. All right. And then the last topic in chapter 2 was on comparing different sets of data. And this is our first introduction into what's called a z-score. The standard deviation is useful when comparing data values that come from different data sets. If the data sets have different means and standard deviations, then comparing the data values directly can be misleading. In such cases, we calculate the z-score for each value. For each data value, calculate how many standard deviations away from its mean the value is. So that's what the z-score tells you. So you've taken a set of data, you've calculated the mean, and you've calculated the standard deviation. Now you can look at a particular data value in your set of data and determine how many standard deviations from the mean that particular data value is. So what you do is you take your data value and you subtract from it the mean. Then you divide that by the standard deviation. And that tells you how many standard deviations from the mean that particular data value is. For a sample, you use the average of that sample, X bar, and the standard deviation of that sample, S. If it's a population, you use the mean of the population, which we represent using the Greek letter mu, and the standard deviation of the population, which we represent using sigma. So the formula is the same whether you're using a sample or a population. You just use a different statistic if it's a sample or if it's a population. Okay. For example, two students, John and Allie, from different high schools wanted to find out who had the highest GPA when compared to his school. Which student had the highest GPA when compared to his school? So John's GPA was 2.85. The school's mean GPA was 3, and the standard deviation of his school's GPA is 0.7. So the mean is higher, but the standard deviation is lower than the other school who measures GPA differently. They measure GPA based on a, looks like 1 to 100 scale. So Allie's GPA was 77. So the school's mean GPA is 80 and the school standard deviation is 10. So it's really difficult to compare, whose GPA is better when we're using different. However, we can use z-scores. So to find the z-score for John, we take his GPA, 2.85, we subtract the mean GPA of his school, 3, and we divide it by 0.7, the standard deviation of his school. So John's z-score is minus 0.21, which means his GPA is 0.21 standard deviations below the mean. So this negative means that his GPA is below the school's average GPA. So he's I keep saying 2.1, 0.21 standard deviations below the mean. 0.21 standard deviations below the mean. Now, Allie, when we find his z-score, we take his GPA 77, we subtract the school mean, which is 80, and we divide by the standard deviation of his school, which is 10, and we get negative 0.3. This means that he is 0.3 standard deviations below his school's mean. So his GPA is below the school mean. His GPA is below the school mean, and it's below the school mean by 0.3. So he's 0.3 below the school standard deviation. So who's got a better GPA? Well, John, because John is 0.21 below the mean, and Allie is 0.3 below the mean. So he's farther from the mean to the left than John. So John's GPA is better. And that's the end of chapter 2. Woohoo! Okay, we're going to start chapter 3 on probability. And just like most chapters in statistics, when we start a chapter, we spend quite a bit of time on definitions. So the first section or so of this is pretty wordy. We're going to start probability. So by the end of this chapter, we should be able to understand and use the terminology of probability, determine whether two events are mutually exclusive and whether two events are independent. So we need to understand the definition of mutually exclusive and the definition of independent. Then we're going to get the addition and multiplication rules for probability. Then we'll look at contingency tables. We'll talk about Venn diagrams as we go along. And then we'll do a tree diagram. And a tree diagram is a way of creating a sample space for us when we have an experiment. So whatever experiment we are conducting in statistics, if we need to know all the possible outcomes of that experiment, we can do that using a tree diagram. All right, I put this slide in the chapter 3 PowerPoint because not everyone is familiar with these two items that are used in games of chance. But we use these examples all the time in probability and make an assumption that everyone knows what they are, and that is not necessarily the case. So the first thing that we use as an example or an item in an experiment quite often is a die. And a die is a cube, three-dimensional shape, it's a cube, and each side of this cube has a number on it, and the numbers range from 1 to 6. So you got a cube has 6 sides. Each side has a number on it. We start with the number 1 and we go to 6. So when you roll a die, you roll a single die, one of 6 values can come up when you roll it. A 1, a 2, a 3, a 4, a 5, or a 6. The other item that we use quite frequently when we talk about probability and outcomes in an experiment is a deck of cards. So a deck of cards is 52 cards in 4 suits. So we break these 52 cards into 4 different suits of cards. And those are clubs. So that little 3-dot thing is a club. Spades. And clubs and spades are black cards. So they are black. Then we have 2 suits of red cards. Holy moly. And our 2 suits of red cards are hearts and diamonds. So we have, out of our 52 cards, 26 of them are black and 26 of them are red. 13 of them are clubs, 13 are spades, 13 are hearts, and 13 are diamonds. In each suit, we have number cards, 1 through 10. So the ace is a 1. So we have 10 number cards, 1 through 10, and 3 face cards. And those face cards are jacks. And the J stands for jack. That's how you know he's a jack. Queen. So it's a female looking character and it's got a Q on it. So that's a queen. And then the king. So we have 10 number cards, 1 through 10, and 3 face cards, jack, queen, and king. So that is the standard deck of playing cards. Standard deck of playing cards also includes 2 jokers, but we are not going to utilize the jokers in our games of chance. We're just going to use the 52 standard playing cards. All right, let's introduce some terminology. The first term that we need to know what it means is probability. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. So how certain are we that we're going to get a queen if we draw 1 card from a deck of standard playing cards? An experiment is a planned operation carried out under controlled conditions. And it can be as simple as shuffling that deck of cards and pulling out a card, or flipping a coin, or it can be as complicated as looking at the growing rates of different corn varieties in a field in Oklahoma. So it can be, or looking at the, I just got that infusion, the success rate or the mitigation of symptoms of patients getting the infusion. And I'm hoping that they will call me and talk to me so that I can be added to their data set that I received that infusion and how it affected my symptoms. So it can be as easy as, like I said, pulling a card from a deck, or as complicated as looking at the data of patients receiving an infusion if they're COVID-19 positive. If the result is not predetermined, then the experiment is said to be a chance experiment. In our example of a chance experiment is the 2 that I've talked about, drawing a card from a deck of 52 playing cards or flipping a coin. Since I don't know when I flip a coin what I'm going to get, am I going to get a head or a tail? That is a chance experiment because I don't know what the result is going to be. The result of an experiment is called an outcome. The sample space of an experiment is all the possible outcomes. The way to represent a sample space is you can just list the different outcomes, or you can create a tree diagram, which we will do at the end of this chapter, or you can create a Venn diagram. And a Venn diagram we'll look at in just a minute. It's just an easy way to represent your sample space using circles and boxes. When you have a sample space, we use the variable S as a capital S to denote that sample space. So for example, if you flip a fair coin, there are two possible outcomes if you flip a coin, a fair coin. You can either get a head or you can get a tail. So your sample space consists of the two outcomes, a head or a tail. And we denote this using set notation. So the braces mean that this is a set. This is a set of outcomes. And we separate the outcomes using commas. So if you flip a fair coin, the sample space, one fair coin, if you flip one fair coin, the sample space consists of you either get a head or you get a tail. An event is a combination of outcomes. And we use capital letters like A and B to represent events. So, for example, if you flip a fair coin, event A may be that you get a head. So A would be the event that you flip a coin and you get a head. The probability of you getting a head is written as P parenthesis A. So this means the probability in our case, event A is getting a head. So this is the probability of getting a head on a single flip of the coin. Now, we talked about this a little bit in chapter 2 when we talked about relative frequency. The probability of any outcome is the long-term relative frequency of that outcome. And how do you calculate relative frequency again? So let's just do a really simple example. Let's say we have data values 1, 2, and 3. And the frequency of those data values is 5, 7, and 6. I'm just making this up. So the total frequency is 18. Is that right? Yeah, that's right. So the relative frequency is 5 over 18, 7 over 18, and 6 over 18. So the probability of a particular outcome is that long-term relative frequency. So the probability of me getting a 1 in this particular set of data is 5 out of 18. The probability of me getting a 2 is 7 out of 18. The probability of me getting a 3 is 6 out of 18. Probabilities are always between 0 and 1. You can never get a negative probability. You can never get a probability that's larger than 1. So every time you hear a coach say, my players gave 150%, no, they can't do that. You can only give 100%. That's all you got. You can't give 150%. You can't. And you can't get a probability less than 0. So you can't get negative probabilities. Ask me sometime about missing 25 points on a statistics exam because I calculated my probability and I got 1.1 and he gave me 0 points on that problem. Anyway, the probability of A being 0 means that that event cannot happen. So if you get a probability of 0, that means there's no possible way that event can happen. The probability of 1 means that you're certain it's going to happen. That's certainty, it always happens. And a probability of a half means that the event occurring or not occurring is equally likely. So the probability of A being a half means that it's equally likely to occur as to not occur. Okay, events and the probability of events. For example, if you flip one fair coin repeatedly, from 20 to 2,000 to 20,000 times, the relative frequency of heads approaches a half. You would expect if you flip a coin that getting a head or a tail would be equally likely. So if you have equally likely events, the probability is a half. And if you flip that coin multiple times, you would expect that the relative frequency of heads to be close to a half. If you roll a die and the die is fair, you would expect any of the numbers 1 through 6 to occur as likely as any of the other numbers. So you would expect the probability of getting a 1 to be equally as likely as the probability of getting a 2 or a 3 or a 4 or a 5 or 6. If you randomly guess the answer to a true-false question, I mean truly, purely, randomly, no idea, you just guess, the probability of you getting it correct is 50%. You're equally likely to get it correct as you are to get it incorrect. Okay, so to calculate the probability of events, to calculate the probability of an event A when all the outcomes in the sample space are equally likely to occur, you count the number of outcomes for event A and divide by the total number of outcomes in the sample space. So you count the number of times your event A occurs, and you divide that by the entire number in the sample space. For example, if you toss 2 coins, a fair dime and a fair nickel, so you're tossing 2 coins, what would your sample space look like? Well, your dime could be a head and your nickel could be a head. So they could both be heads. That's the first item in your sample space, head, head. You could expect that the dime is a head and the dime is a tail and the nickel is a head. That's the second item in your sample space, tail, head. So the dime is a tail and the nickel is a head. Or you could expect the reverse, that the dime is a head and the nickel is a tail. Last but not least, in your sample space, both of your coins could come up tails. So there are 4 possible outcomes in your sample space. You could get both heads, tail, head, head, tail, or tail, tails. Okay, 4 possible outcomes. So what's the probability of getting 1 head? Exactly 1 head. Well, there are 2 outcomes in your sample space where you get exactly 1 head. If the dime is a tail and the nickel is a head, or if the dime is a head and the nickel is a tail. So there are 2 possible outcomes out of the 4 where you get exactly 1 head. So if A is the event that I get 1 head, A can be these 2 possible outcomes out of my 4 possible outcomes total. So the probability of me getting exactly 1 head is the number of outcomes, that includes 1 head, there are 2 of those, divided by the total outcomes in the sample space, which is 4. So the probability of me getting exactly 1 head when I toss 2 coins, 2 fair coins, is 1/2, 2 out of 4, which is 1/2. Okay, so what if you roll a die? You roll 1 fair 6-sided die with the numbers 1, 2, 3, 4, 5, and 6. So your sample space consists of the set that includes those 6 numbers, 1 through 6. Let the event E be rolling a number that's at least a 5. So what are your possible outcomes if your roll is at least 5? Well, at least 5 would be 5 or more. So 5 or 6. So there are 2 possible outcomes of at least 5. If you roll a 5 or if you roll a 6. So here's our possible outcomes. Out of our total sample space, there are 6 items in our sample space. So there are 6 possible outcomes total, 2 of which are at least 5. So the probability of event E rolling at least a 5 is the 2 outcomes, a 5 or a 6, divided by the total number in our sample space, which is 6. Now, if you rolled a die only a few times, I mean, have you played Yahtzee? You wouldn't expect, exactly 1/3 of the time to get a 5 or a 6. However, if you rolled this die a significant number of times, you would expect the probability of getting a 5 or a 6 to approach 2/6 or 1/3. The long-term relative frequency of obtaining this result would approach the theoretical probability of 2/6. So this is called a theoretical probability. When we look at all the top possible outcomes of that event and we divide it by the samples, the total in the sample space, that is a theoretical probability. You could do an experimental probability by rolling the die multiple times and counting the number of times you get a 5 or a 6. Okay, so for example, you have a jar with 150 jelly beans in it. I don't like jelly beans. So. And the taste thing, the losing of your taste, the only 2 tastes I can taste are bitter and sweet. Everything else doesn't taste like anything. That's kind of weird. But I can taste sweet and I can taste bitter. So I can taste my coffee because my coffee is bitter. All right, so you have 150 jelly beans. 22 of those jelly beans in that jar are red. 38 of those jelly beans in that jar are yellow. 20 are green, 28 are purple, 26 are blue, and the rest are orange. So how many orange I have? Well, you'd have to add the 22, the 38, the 20, the 28, and the 26, whatever that number is, and subtract that from 150, and that would tell you how many of your jelly beans are orange. So if you were to take this jar and mix it up really, really well, so that every jelly bean has exactly the same likelihood of being pulled out of the jar. So we're doing this jumble of jars so that and when I reach in that jelly bean jar, every jelly bean has exactly the same chance of being drawn. What's the probability if B is the event of getting a blue jelly bean? What's the probability of me getting a blue jelly bean out of this jar? Well, there are how many blue jelly beans? There are 26 blue jelly beans in this jar of 150 jelly beans. So the probability of me getting a blue one, there are 26 possible outcomes of blue. Out of 150 items in my sample space, there are 150 items in my jelly bean jar. So the probability of me getting a blue one is 26 out of 150. What's the probability of me getting a green one? Well, there are 20 green jelly beans out of the 150 jelly beans in the jar. So the probability of me getting a green one is 20 out of 150. What's the probability of me getting an orange? Well, I have to figure out how many orange jelly beans are in this jar. So if I take the 22, the 38, the 20, the 28, and the 26, and I add it up, and I subtract that from 150, I see there are 16 orange jelly beans in my jar. So the probability of me getting an orange jelly bean is 16 out of 150. What's the probability of me getting a purple jelly bean? Well, there are 28 purple jelly beans in the jar, so 28 out of 150. What's the probability of me getting a red? Well, 22 out of 150, and the probability of a yellow would be 38 out of 150. Now, you'll notice we write these probabilities as fractions, not necessarily simplified fractions, or we could find a decimal approximation. Just be sure that in My Open Math, you read the instructions. If nothing else, leave it as a fraction. And then if they tell you that you need to round it off to 4 decimal places, find a decimal equivalent to it. But normally we just leave our probabilities in terms of fractions. Okay, so let's talk about fair. And we talked about this early in the semester. We're in the 4th week already. Can you believe that? And my question was, because we were in the middle of playoffs, college playoffs, as a matter of fact, we're getting ready in a week to see the Super Bowl. Go Chiefs. Editorial comment, go Chiefs. And I said, how do they know that big old coin they're flipping in the college football championship was fair? And I hope that somebody did an experiment like this guy did to see if coins are fair or not. So 2 math professors in Europe had their statistics students, and I should do this some semester. I should have you guys flip coins and see if a nickel is fair. But they had students test the Belgian €1 coin and discovered that in 250 trials, a head was obtained 56% of the time, and a tail was obtained 44% of the time. I'm thinking that coin's not fair. I'm thinking that heads has a greater probability of coming up than a tail. So if you're betting somebody using a Belgian €1 coin, bet heads. Use heads, say pick heads. So the coin may or may not be balanced. And we talked about this also, that dice may or may not be balanced. So the die that you roll when you're playing Yahtzee are not, chances are, unless you specifically buy die that are balanced. So if you're playing, though, at a casino, you're playing dice, their dice have to be balanced. Otherwise, they're going to get sued. And so what they do is they take, once they remove the divots in their die, they fill the divots level using paint that's the same density as the die. So truly, a 1 has exactly the same probability of being rolled as a 6. And they have to do this, otherwise someone's going to come in there and discover their die is not fair and that they're cheating customers, and that would be a bad thing if you were a casino. That would put you out of business. Cheating customers is not how you're going to stay in business. The fact of the matter is, looking at probability, games of chance, the casino is always going to win. I mean, you may occasionally win, but the probability says that most of the time they're going to win. That's how they stay in business, because you're going to lose. All right. Example. Let's look at an example. What happens if the probabilities are not equally likely? Well, then we're going to get techniques later in this chapter to deal with this kind of outcome. So the probability that a particular knee surgery is successful is 0.85. So 85% of the time when this knee surgery is performed, it's considered successful. Whatever their measure of success is, it's successful. Find the probability that 2 knee surgeries are successful. So what are the possible outcomes if you perform 2 knee surgeries? Well, they could both be successful. Or the first surgery could be successful and the second surgery deemed a failure, whatever their measure of success and failure is. The third outcome could be that the first surgery was a failure and the second surgery was a success. And the fourth possible outcome in this scenario would be that both surgeries were failures. So, however, the probability of getting 2 successes, and a success and a failure, or a failure and a success, or a failure and a failure, those 4 probabilities are not the same. Because the probability of a success or a failure, they're not equally likely. It's more likely that your surgery is going to be a success. So the probability of getting 2 successes, what do we have? 2 outcomes that represent 2 successes, 1 outcome, is not a fourth, because these four outcomes are not equally likely to happen. A success in this surgery is more likely than a failure. So it's not a 50-50 chance that you're successful or fail or it's a failure. Would you do surgery if it's? I wouldn't. So we need to talk about more additional probability rules to be able to do this example. Okay, so let's talk about and or events. We have A or B event. That means either A or B occurs. And then we have an A and B event. That means both A and B occur. So the first is one or the other occurs. The second is they both have to occur. Okay, an outcome is an event, A or B, if the outcome is in A or is in B or is in both A and B. For example, let A be the event that consists of the items 1 through 5, and B be the set of outcomes 4 through 8. Then A or B is the union of those two sets. Which means we join the two sets together. Sorry, man, out of room. Join together. So if we take the set A and we take the set B and we join those two sets together, we get the set A or B. 1, 2, 3, 4, 5, 6, 7, 8. Now you'll notice that we don't, both set A and set B contain the numbers 4 and 5, and we don't repeat those. We just list those numbers once. So to join these two sets together, we just stick them together. So we take all the elements in A, 1, 2, 3, 4, and 5, and we add to that the elements in B. So we have 4, 5, we don't repeat that, but we do have elements 6, 7, and 8. So A or B is the set 1, 2, 3, 4, 5, 6, 7, and 8. Now an outcome A and B is an outcome that occurs in both A and B at the same time. So an or is a union, an and is an intersection. It's the elements the two sets have in common. So if we have the set A as 1, 2, 3, 4, and 5, and set B is 4, 5, 6, 7, and 8, what elements do those two sets have in common? Well, they have what? The 4 and the 5. So those were the two elements we didn't repeat when we joined them with an or. So those two elements that we don't repeat, those two elements that overlap the two sets, are the elements in the and. So the and, the intersection where the two sets overlap, would be the set 4 and 5. The complement of an event A is denoted using A prime. That is a prime symbol. Or in my open math, in some of your problems, they use A superscript C. That means the complement of whatever event A is. A prime or A complement consists of all the outcomes in your sample space that are not in A. And the probability of A occurring plus the probability of the complement of A occurring is always equal to 1. So the probability of A plus the probability of A complement is always equal to the number 1. For example, my sample space consists of the numbers 1 through 6. Let A be the event that consists of the outcomes 1, 2, 3, and 4. So my sample space are the numbers 1 through 6, and my event A consists of the outcomes in that sample space of 1, 2, 3, and 4. A complement is the set of outcomes that are in my sample space S that are not in A. So what are in S that are not in A? Well, we got a 5 and a 6. There's a 5 and a 6 in my sample space that's not in event A. So A complement is the set that consists of 5 and 6. Now the probability of A occurring, since we have 4 outcomes in event A, divided by my number in my sample space, which is 6, the probability of A occurring is 4 out of 6. The probability of A prime occurring, there are 2 outcomes in A prime, 5 and 6, out of the entire sample space, 6. So that would be 2 out of 6, 2 outcomes out of a sample space of 6. So 4 6 and 2 6, if you add those together, you get 1. 6 over 6 is 1. So the probability of an event A occurring plus the probability of the complement of A occurring is always equal to 1. And the complement of an event are the items in the sample space that are not in my event. Okay. Conditional probability. Conditional probability is the probability of an event occurring given another event has already occurred. So the conditional probability of A given B is written. We write this as P, parenthesis, A, vertical bar, B. And what this means is the probability of event B occurring given A has already occurred. So it's the probability of an event B occurring given A has already happened. So the probability of A given B, that's the way we read this, probability of A given B is the probability that event A will occur given that event B has already occurred. A conditional reduces the sample space. So it reduces the size of your sample space because one event has to have already occurred before the second event can occur. And we calculate the probability of A from the reduced sample space B, for example. So suppose we toss one fair 6-sided die. The sample space of this experiment are the numbers 1 through 6, or the sample space is the numbers 1 through 6. So the sample space S consists of the set that consists of the numbers 1, 2, 3, 4, 5, and 6. So let A be the event that the face is either a 2 or a 3. So event A is that you roll a 2 or a 3. Event B is that the face is a 2, a 4, or a 6. So event B is the outcomes that you roll a 2, a 4, or a 6, an even number. So event A is that you roll a 2 or a 3. Event B is that you roll an even number. So calculate the probability of A given B, that you get a 2 or a 3 given you've rolled an even number. So you count the number of outcomes in event A. You got a 2 or a 3. But the sample space B is that you roll an even number. So your sample space is now 3. So what's the probability of me getting a 2 or a 3 given I've rolled a 2, 4, or 6 already? Well, there's only one outcome in my sample space B that fits the criteria of getting a 2 or a 3. So event B is that I roll an even number. Event A is that I get a 2 or a 3. So what's the probability of me getting a 2 or a 3 given I've rolled an even number? Well, there's only one outcome in my event B. That's an even number. That's a 2 or a 3, and that's this 2 right here. So the probability of me getting a 2 or a 3 given that I've rolled an even number is only 1 out of 3. So we've reduced the sample space to 3 because there are only 3 possible ways I can roll an even number. And of those 3 possible ways I can roll an even number, there's only one possible way I can get a 2, and that's if I roll a 2. But we need a formula for those. This is called
Can you
Bayes.
explain that one more time?
Sure. All right. The probability of A given B is the probability of getting A, which is a 2 or a 3, given I rolled an even number, a 2, a 4, or 6. So what's the probability of me getting a 2 or a 3 if my sample space consists of 2, 4, and 6? Well, there's only one outcome that's a 2 or a 3 in my sample space. That's when I roll a 2. What's the total number of outcomes in my sample space? Well, there are 3. So the probability of me rolling a 2 or a 3, given I've already rolled an even number, is only one outcome out of 3. Okay, so the first,
Okay, thanks.
is that better?
Yes, thank you.
You're welcome. Okay, so you have a formula for it, which we need to explain the parts of this formula. This is called Bayes' theorem. 18th century British mathematician Thomas Bayes, and it's the mathematical formula for determining the conditional probability. And what he says is that the probability of A given B, so the probability of event A occurring given B has already occurred, can be found by the probability of A intersect B over the probability of B. So let's define what this means. So that symbol there, that upside down U, means intersection. Or it means and. So the probability of A intersect B is the same as the probability of A and B occurring. And then you take that probability and you divide it by the probability of B occurring. So the probability of A given B is the probability of A and B occurring divided by the probability of B occurring. You can also write this using Bayes' theorem as the probability of A given B is the probability of A occurring times the probability of B given A. So the probability of B occurring, which I can't say today, given that A has already occurred, divided by the probability of B. Now, I know this formula looks kind of complicated right now, but we're going to do an example later and we'll break down each of these probabilities and show you how this is a fairly simple formula to use to find the conditional probability. And what's a conditional probability again? A conditional probability is the probability of an event occurring given another event has already occurred. I don't know if I'm going to do this example yet. Yeah, let's go ahead and talk about this before we talk about 3.2. So let's talk about cards. So if I have a deck of 52 cards and I draw one card out, what's the probability of me getting a queen? Well, there are 52 possible outcomes in my sample space. I could draw one of 52 cards. But 4 of those outcomes are queens. I could get a queen of hearts, a queen of diamonds, a queen of clubs, or a queen of spades. So there are 4 possible outcomes that are queens. All right? So that's the probability of me getting a queen. Now let's say I take that card and I put it back in the deck. Shuffle them up again. What's the probability of me getting a queen? Same thing. So one event didn't depend on what the other event was. So if I replace the card, I don't have a conditional probability. The second event doesn't depend on the first event. But what if I don't? Well, now me drawing a queen out of that deck of cards is conditional to me drawing a queen out the first time. So now what's the probability of me drawing a queen out? Well, if I drew a queen out the first time, so the first event was successful, then the conditional probability of me drawing a queen, given I've already drawn a queen out of the deck, is affected. Now there are only 3 queens in the deck. And there are only 51 cards in the deck. So this is a conditional probability because the second event is conditional on what happened in the first event. So the probability of me drawing a queen the second time, given I drew a queen out the first time, is affected. So my probability is 3 out of 51. All right. All right. So let's talk about what time do I have? Probably a good place to quit. This is probably a good place to stop. We talked about quite a bit, let it all sink in, and we'll pick up section 3.2 on Thursday. That's a really good stopping place. Are there any questions? Okay, if you haven't typed your name into chat so I can take roll, would you please do that? And if there aren't any questions, then we will talk to you on Thursday. Have a good rest of your day.
Hello, ma'am. Hello, ma'am.
No, ma'am? All right.
Yes, this is Tessie. Please, can you just open the unlock, what's it called? Unlock.
Look at honor lock.
Yes, I need the password. I'm sorry, I wanted to do it. I don't know, it's due
No
already.
password. You don't have a password.
But he's asking for password though. So what should I do?
What do you do? Let me show you.
Okay.
Okay, I'm gonna turn my camera off. Actually, I don't know if I need to, but we're gonna turn the camera off.
Okay.
Okay, so what you do, I don't think I have an ID in here. I don't have my ID in here. Okay, so what you do
Mhm.
is you open the practice test. Just open it up.
Mhm.
And it is, I've already done this. Let's do student preview. Oh, why is it opening for me? It's because I'm a teacher. All right, just a second. Let me go in as a student. I forgot. All right, try this again. So I'm going to go to tests. And I'm going to open that practice test up. And I've already taken it, so that's why it's doing this to me. So if I hadn't taken it, it's going to open up and wait for a password. Okay.
Okay.
Sorry about that. I've already taken it in this class. So then I open, now that I have it open, I open the HonorLock LTI. And it's missing. Well, no wonder you can't take it. Let me fix that. Let me stop share. I apparently set the due date. All right. All right. All right, it closed. I'm going to reset that so it's open again.
Thank you.
I'm going to open it up for another week. So it's going to open till the 9th. Okay, let me go into my open math and make sure I got the due date set. So that was due the 26th, right?
Mhm.
Let me go back a month to the 26th. And let me set that to be due to the 9th. Save that. Okay, so now it should be available for you to take.
Okay.
And what you do
Mhm.
is you open the exam, and it's going to be sitting there waiting for a password.
Mhm.
Then you go to HonorLock
Mhm.
and you launch the HonorLock LTI.
Mhm.
You find that test, that practice, and you hit launch. And you
Okay.
have to take your picture, show your ID and all that stuff. And then once you have all that done, you have the HonorLock window and your
Mhm.
test window, and you tell HonorLock to submit your password.
Okay.
Okay.
Yes, ma'am. Thank you.